Hey all, how's it going? I'm going to make this video in compensation for the fact that I forgot to record today in class for the lecture. So I just thought I could flesh it out, make a lot more details better explained here now that I have some time to think about what I'm going to say, go over the material in a more controlled manner, kind of explain things in a way that, at least to me, makes a little bit more sense. Again, I'm not the smartest person, so I try to break it down to in your boilerplate, hey, if you follow these steps, you really can't go wrong kind of method. So the thing that we're going to be covering today is the direct method for bar elements. So in other words, you have some kind of steel beam, metal beam, whatever have you. It could be cylindrical, it could be square. But long story short is that if you compress it, if you put a load that makes it under tension, bend it, whatever scenario, if it behaves under Hooke's law, i.e., when you unload it, it will snap back into its original place, so it behaves kind of like a spring. We can essentially approximate everything as such. Also, sorry for the background noise. I don't know how much I can edit and post. I tried moving down to essentially a study room in my apartment complex, but we'll see how well the audio quality comes through. But what can you do? Anyways, so let's kind of go over a brief overview on how to look at these elements, right? So essentially, whenever you see these beams in the problems, understand that so long as they're behaving under Hooke's law, so they're not plastically deforming, they're deforming elastically, i.e., you unload it under whatever external force you have, it will go back into its original position. You can treat it as if it is a spring, right? So the spring constant, this K constant, is given by the product, the Young's modulus E times its cross-sectional area, all divided by the length of the beam, right? So you can see here I've kind of made it into a diagram. So it's being loaded by some force Q, and then you will have internal responsive forces, F subscript I, superscript E, where E here is the spring in question, and I and J are denoted by the nodes. Okay, so in general, these are responsive forces, so it's a good idea to just draw them pointing to the left. If you solve it and you find out that, hey, these forces are in fact to the right for whatever reason, well, great, the math will take care of it. But for diagram's sake, just make sure you draw them pointing to the left. Whether or not Q is pointed to the right, to the left, is 0. You should just get by on drawing these pointing to the left, okay? So this u sub I, u sub j, that is some kind of displacement at these nodes, so nodal displacement, right? And let's continue. So you guys might have seen this equation in class. So if you essentially work out the matrix math, you'll see that it behaves much like k delta x, right? So this delta x that you've seen in like physics 1 is just the difference in displacements, right? So you could see here for before, so when I see before spring, after spring, here's a spring. The node before the spring will have the internal force of this value. And then after the spring, you'll have F sub j, you will have this value. And you'll notice that it is just the negative of the before spring. And why is that? Well, it turns out I kind of lied a little bit. The after the spring is actually supposed to be pointing to the right. However, I don't want to give you guys any kind of confusion. So we just will say, hey, it's just pointing to the left, and we'll just keep this little factoid to ourselves. Try not to confuse yourselves, and if anything, you could just memory wipe yourself from the last 20 seconds. Just know that your internal force members for every spring will point to the left, okay? So if you see a spring, you should have an internal force on the left side and on the right side. Okay, so let's look at our first example. Essentially, here's your real system that we have. It is a cylindrical solid rod of two different cross-sectional areas, and we apply a force to the right at this intersection here. Okay. Now you might ask yourself, getting ahead a little bit, what happens if we apply a force somewhere in the middle of the rod? Don't worry, we'll cover that. But for now, let's just deal with this case here. Okay. So if you look at the model to the right, the discrete method kind of simplifies it a little bit, cleans it up. However, we can make this look even simpler. Look at that animation. Hollywood, start hiring me. Anyways, so what we can do is we can treat this as two springs, right? So here's the small rod, here is the large rod, and we have three nodes. One node is at the wall, another node is at the intersection, which also happens to be where the force is applied, and then the third node is at the wall, okay? So we need to calculate the K constants. I told you previously how the K constants were calculated. So for each rod has its own Young's modulus cross-sectional area and total length. So we can see here the K1, K2 constants are given. And I'm going to keep the equations for the internal forces about the springs to the right. So let's work through this. Let's do a sum of force at each node. So one thing I should mention as well, sorry for that, you will also have reaction forces at the walls because this is a statics problem. Nothing should be moving. I am just going to assume that these reaction forces are moving to the right or pointed to the right. If I end up being wrong in the direction, I'll end up with a negative value and nothing's really lost. We'll just say, oh, okay, if it's a negative value, I'll end up pointing to the left. We'll see what that looks like later. Anyways, so let's walk through and do a sum of forces at each node. So for node 1, we have R1 pointing to the right, and then we have F11 pointing to the left, right? So then node 2, you could see here, we have F pointing to the right, and after our first spring, we have to make sure we do our after spring value here. And then we have another spring here, so we have to do a before spring value. So now if we look at the sum of forces, we have F12 and F22. So we have two internal force members here equals one external force. And then we do the same thing on the third node here, where it's just force at the wall is equal to the internal force F23. Real easy, simple stuff. So now what I'm going to do is I'm going to apply some values to that. So again, I wrote out these sum of forces, but it might be confusing. Well, what values go where? Just remember where these forces are in relation to the spring. So for example, here is K1. You can see here, then F11 is using the before spring value, where E is 1, U of I is U sub 1, U sub j is U sub 2, and so on and so forth. So you could see how we built up our system of equations. So we have our system of equations, but what values do we use? We're kind of stuck right now. Well, one thing we should do is use boundary conditions. Ideally, your walls shouldn't move. If things are moving, you might have bigger issues in play, but for now, we're just going to assume that your walls aren't moving. So that means your nodal displacement, U1 and U3, will be 0. Okay, so let's just apply these values, and hey, look at that. These simplify down really easily. Now you'll notice that I have equation 2 circled. Okay, why? Well, I don't know what U2 is, I don't know what R1 is, I don't know what R2 is, so those equations don't really help me. The only real thing I do know is the value of F, K1, and K2. So real easy, breezy, beautiful. Cover girl, we can solve for U2, and you can see we get the values. What is that? That's about 100 microns. So a very small movement, which makes sense. For 100 gigapascals, about 10,000 newtons, we wouldn't expect our beams to deflect and move that much. Similarly, all we have to do, now that we have the values of U2, we can calculate the values and directions for the reaction forces. So we see here we have a negative value. So all that negative value means, if we look up here to R1 and R2, well, that just means we were applying it in the wrong direction. So these negative values mean that, hey, it's actually applying to the left, which makes sense, right? Because it's a statics problem. You need something, an external force, to stop the motion. So it'll have to be applying to the left. So I told you what happens if, say, we have a force member, or like a force being applied in the middle of a member somewhere inside that's not on the end. Well, that's easy. All you gotta do is split up your springs, right? So we can create a node at the wall still. Let's make another node where the force is being applied, another node where the area changes, and then a fourth node at the wall again. Okay. You will have to calculate the spring constants in between these nodes, right? Because you split it up. Luckily, it's at the midpoint, so it is just half of what this total K value is. But you could see here how your nodal analysis will start to change. Okay, so again, if you're doing a sum of forces, understand that it would be R1 is equal to F11. For node 2, you have your external force is equal to F12, F22. Here is kind of interesting, right at this intersection here. It's going to be 0 is equal to F23 plus F33, and then finally R2 is equal to F34, right? Real easy stuff. Actually, it's not really easy stuff. This took me a while to understand on my own, so if you're not immediately getting it, just try to work it out. Come back to this page, or this slide, and see if it makes a little more sense. If it doesn't, there's always my office hours and email, or the comment sections below. All right, so let's mosey on through. Let's get another example. So this example essentially has multiple elements loaded on a singular node where it might not look like it makes much sense. So in the other previous examples, we had 2 springs, 1 node, which is a lot more easy to understand. But here we have 3 springs and 1 node. So how do we handle that? Well, as you can see written up here, and I think that's orange text, brown, definitely not red. I don't know, color blindness is tricky. You can see how we can simplify this further, where your second node is kind of hard because we're trying to draw this in 2D space, just encapsulates multiple force members. Okay, so let's break this up. So you can see here, I split it up into 3 springs. 2 springs share this large node here. We have 1 force on the left-hand side, and then we have 2 nodes that lie on the same wall. Okay, so take a second and try to figure out where you're going to draw your internal force members, or your internal forces. Okay, so hopefully you kind of thought about maybe pausing it. Oh, I'm not you. Anyways, here, so let's walk it through. Okay, so we have our first spring, so I'm going to do a before and after, so F11, F12. Then we're going to go up here and look at our second spring, so we should have F22, F23. And then all the way down here we have our third spring, so it should be F32 and F34. Okay? So that's where those values come from. Mind you, we don't know the exact displacement values just yet, but we know that we'll have a nodal move or displacement at 1, this entire second element 2, and then another one at 3 and 4. Again, we know the boundary conditions is this won't move, but for now, let's pretend that it might move. We don't exactly know. Another thing that you might be wondering is, wait a minute, you're going to have some external forces, right? Some response forces in the y directions. Yeah, they cancel out technically. We want to keep this as a one-dimensional system right now for video's sake. Otherwise, it's going to be extremely painful, and I would recommend you use ANSYS, Excel, crying, I don't know. But for now, we're just going to use a little bit of a simplified case, okay? So let's do a sum of forces at each node. So node 1, really easy. F is equal to F11. And then node 2, we see here, our our net external force is 0, so we have 0 is equal to F12, F22, and F32. Node 3, we have R3 is equal to F23, and node 4, R4 is equal to F34. Okay, so I'm going to use these equations just to set up what these values will be. And as you can see here, we have a lot of values put in. And let's apply some boundary conditions. So once again, your walls shouldn't be moving. So U3 and U4 will be 0. So these equations can simplify down to the following, right? So you see here, there's no U3, U4, and the only things that we are interested in is U1, U2, R3, and R4. However, you notice we don't know what R3 is, we don't know what R4 is, we don't know what U2 is. So therefore, the only thing that we can really deal with is two equations with two unknowns, U1 and U2. So we can solve these either using a system of equations. So you could just do the matrix math, easily find the inverse of that, and you can find the values for U1 and U2. Or you could just do it algebraically and solve for U1 in terms of U2 and then solve for U2. Either way, these are the values that you will get. So as you can see, it's pretty straightforward. I try to make these that's a bit more boilerplate-y, so you essentially just plug in values, you just run with it, and everything should work out, okay? You might be wondering, well, hey, what happens if I want to apply some external force here at node 2? And let's say I'm going to apply it to the left along with all these force members. What do I do? Well, let's call this force Q. So on this left side here, you would just write negative Q. Negative because it's moving to the left. And since it's an external force, just put it on the opposite side of your internal forces. So yeah, that should set you all up for your homework assignment. And if you don't have a homework assignment, you just stumbled upon this video, welcome. Hope you learned something. Hopefully I taught it well enough. And if you have any questions, comments, concerns, or personal life philosophies you want to share with me, or ways I can improve, just email me, talk to me in the hallways, or leave a comment down below. Anyways, all right guys, I will see you next time.